I'll be sending you the videos as well. So when we talk about dimensional analysis, what we mean is that we are expressing a given quantity in terms of the base quantities or the fundamental quantities. So expressing a given quantity in terms of the base of fundamental quantities S is what the concept dimensional analysis is about. Expressing a given quantity in terms of the base of fundamental quantities is what we mean by dimensional analysis. Okay, now let me probe further to find out how you understand base quantities. Can you discuss or talk about the base quantities we have in physics? What and what constitute? So we have mass. So base quantities as against base unit. What is the corresponding unit?
Kilograms.
Kilogram. Okay. So kilogram. How do we write the short form notation of kilogram?
kg in small letters.
So we have to be specific. Small letter K, small letter G. Okay. If you just go by kg, it's an open statement. Okay, so 1, 2. We are discussing the base quantities and the corresponding base units. Mass is 1, 2.
Length.
Okay. Length. What is the corresponding base unit?
Meters.
Good. Meters.
Small
what is the small m? Good. 3. The third base quantity. Not in that exact form.
Time.
Or order. Time. Good. Time is the next or another corresponding unit.
Seconds.
Good. Second. The second
is a small
short
s.
Small letter S. Then 4.
Electric
current. Electric current. What is the unit?
Ampere. Capital letter E.
You see, ampere, the unit ampere is small letter E, M-P-E-R-E. And the unit is capital E. Yes. Somebody's hand is up. Zoom user. I'm coming. Somebody's hand is up. Please go ahead and ask your question. Pressure is not a base unit.
Yes.
Pressure is not a base unit. Let me explain why we indicate this as small letter A and not. You see, ampere is a unit that was added to somebody. So if you are referring to the person ampere, then you start with capital letter A. But when you are referring to the unit ampere, you begin with small letter A. Okay, all the units are all the honorary units, such as Newton, Pascal, ampere, What? Help me. All those honorary units. Joule. If you are referring to the unit,
What?
you must begin with small letter. But if you are referring to the person, capital letter. Is that okay?
Yes, sir.
Yes, sir.
So that's the difference. Yes, we are discussing base unit. 5.
Luminous intensity.
Luminous intensity. Luminous intensity. What's the unit?
Candela.
Candela.
Okay. Candela. How do we represent? What's the short form notation?
Small letter C, small letter D.
Okay. 6. Base unit. How many base units do we have in all?
7.
7. Okay. So
Temperature.
Temperature. Good. Temperature. Temperature. What's the SI unit?
K.
Kelvin. Say Kelvin.
Kelvin.
Kelvin. Okay. And why not degrees Celsius?
Or degrees Celsius.
Why not degrees Celsius but Kelvin? Please mute yourself, okay? If you want to speak, you then unmute. Why not degrees Celsius but Kelvin? Okay, so it's similar to the meter and other units such as centimeter, millimeter, and so on and so forth. Okay, we have subunits. So SI unit for temperature is a Kelvin, but other units are the degree Celsius, Fahrenheit, okay, degree Fahrenheit, and so on and so forth. All right, what's the 7th base unit?
Amount of substance.
Most substances.
Come
Amount
again.
of substance.
So amount of substance.
Most substance.
Amount of substance.
If I don't open that, you will chop me. I'm not supposed to be crying.
Please mute yourself. If you haven't muted, please do so. Let me check attendance. So I have Ofei is here, Zoom user, and I don't know if that is Benedict. Emmanuel is here, another Zoom user, Anefi, Cromwell, Justin upon 2 other Zoom users. All right. So next time you have to send your names to me. Okay, I have to identify every individual. What's the SI unit of amount of substance?
Mole.
Mole. Shortened as MOL. Good. So these are the 7 base of fundamental units. Okay, so when we talk about dimensional analysis, all that we are actually saying is that we want to express a given quantity in terms of them, in terms of the base quantities. Okay, so expressing a given quantity in terms of the base or fundamental quantities are what or is what embodies dimensional analysis. But then at your level, at the SHS level, the dimensions of a given quantity are mainly expressed in terms of mass, length, and time. But at the university level, we can express a given quantity in terms of the 7 base or basic quantity or fundamental quantities. But at your level, we don't open it, we restrict. That is how come in school you were only using these 3. Class, are you okay?
Yeah.
The dimension of mass. the dimension of a given quantity. Example, Benedict. If I want to express the dimension of Benedict, the rule is that produce a square bracket and put the quantity Benedict into it. So when you do this, every physics person, okay, can be able to, read or say that this is the dimension of Benedict. So the dimension of mass must be put into a square bracket to denote that this is the dimension of mass, and it is represented by capital M. The dimension of length represented by capital letter L. The dimension of time represented by capital letter T. Class, are we okay? So this is it. So basically, all that we are saying is that at your level, expressing a given quantity in terms of the base unit, mass, length, and time is what dimensional analysis is about. We are going to try a lot of examples, and then I'll pick WASI questions and then give it to you to try your hands on. Please, is there any question here? Is there any question? Nora, you are welcome.
Thank you.
Okay. All right. Let's look at uses of dimensional analysis before we solve examples. Uses of dimensional analysis. Yes. Can you share that with me? What are some of, Nora, start with us. What are some of the uses of dimensional analysis? Nora, break the ice with us. Uses of dimensional analysis. Do you have any idea? Okay, Cromwell. Cromwell, just crawl so well with this. Cromwell, are you there? All right, let's make it open. Cromwell, you have unmuted, so go ahead. What are some of the uses of dimensional analysis?
Used for checking errors.
Used for checking errors. You are not so far from the truth. But can you be specific, Cromwell?
It's used for checking dimensional errors.
Used for checking dimensional errors. Okay. Used for checking dimensional errors. Justin.
Sir, please, it's used to check the validity of equations.
Okay, so for checking validity, the validity
of equations.
But there is another term to use in place of validity. That's what I'm looking for. Checking validity or correctness. Correctness of a given equation. Nora.
Please, it is used for deriving formulas.
Okay, so she's saying that it's used for deriving formulas or relations between what, Nora? Deriving formulas or or relation between quantities. Okay, so Nora, relation between given quantities. Nora,
Okay.
is that clear?
Yes, please.
Okay, there is another usage of dimensional analysis which you haven't talked about. Yes. Yes. What's the other use of dimensional analysis?
Sir, please, it's used for converting units.
Used for converting units. You are not so wrong, but you are also not so correct. Something is missing. Something is still missing. You still have the chance to make it better. It is used for determining units, especially base units of a given quantity. Okay, so to determine base units, the base unit of a given quantity. So used for checking errors. Yes, the error part goes with validity. Okay, so whoever gave me this answer, that is, it relates to this one, checking validity or correctness of an equation. If an equation is wrong, you see, example, how do we calculate force? How do we calculate a force acting on a body? Can somebody help? If I want to calculate force, how do I calculate that? Or what's the equation for this?
The equation of force is mass of an object and the acceleration due to gravity.
So, yeah, thank you. Mass, sometimes mass times linear acceleration A, and when it's about force with regards to weight, okay, then the weight also becomes mass times acceleration due to gravity. As we move on, you understand what this means and when do we also use this. Okay, this is the actual equation for force. If I make the mistake to express force as mass times length, I can use dimensional analysis to check whether this formula is correct or wrong. Class, is that okay? So we can use that to check correctness or incorrectness of a given equation. And we are going to go through this. Try an example to understand this very well. Okay, then deriving formula or relation between a given quantity. And then the last one, to check the base unit of, or determine the base unit of. Now, what is the SI unit of force? What's the SI unit of force?
Newton.
Oh, Newton. Newton is the name of a famous scientist, Sir Isaac Newton. So the unit Newton is an honorary unit. It was honored to influential scientists. Now, the actual unit of force. So we want to use dimensional analysis to determine the units of their given quantity force. So force into a square bracket. Okay, meaning we are looking for the dimensional representation of force. Before we do that, let's start from what's the dimension of velocity? Then we determine the dimension of acceleration. Then we apply that to the dimension of force. Class, what is velocity?
Displacement over time.
So you are right, but let's be practical. When we talk about velocity, what do we mean? The velocity of a body. What does it mean? Or speed. What is speed? What is speed? What is speed? Okay, so speed is equal to distance over time. Usually distance covered over the time taken to cover that distance. If I want to prove to you, or let's use Cromwell. Supposing Cromwell want to prove to us that he is speedy, or he has speed, how can Cromwell prove that truly he has speed? Cromwell must be given a certain distance. Then we look at the time he will take to cover that distance. So if then Usain Bolt was said to be the fastest man on earth. Why? Because Usain Bolt then could cover 100 meters within about 9.6 seconds. Okay, he could cover 100 meters within 9.6 seconds. Can you imagine? Meanwhile, the same distance, if it is given to Mr. Abia, I can use about 2 minutes to cover. And so, because Usain Bolt could use lesser time to complete that distance, it obviously could tell that he is speedier than Mr. Abia. Class, I hope you are following.
Yes, sir.
So if we want to determine the speed of a body or an object, we look at the distance, okay, and the time taken to cover that distance. So speed is distance over time. Let's determine the dimension of speed. The dimension of distance. What is the dimension of distance? Class, what's the dimension of distance?
L.
L.
Capital L is the same as the dimension of length. Okay, so whether the distance is so short or long, they are all length. So the dimension of distance is capital L, and then the dimension of time is capital T. So this is L T exponent what? Exponent negative 1. This is the dimension of speed. We can use this to determine the SI unit of speed. The L represents distance, length or distance. SI unit of length is meter. The T, capital T, represents time. SI unit of time is the second. So we have M S raised to the power negative 1. Note that is the same as M/S. The value is still the same. Is that okay? So we have used the knowledge of dimension to determine the SI unit of the quantity speed. So knowing the dimension, okay, you can easily determine the unit as well. Now velocity. What's the difference between velocity and speed?
Sir.
Well, yes.
Sir, please, velocity is a vector quantity and Speed is a scalar quantity.
Good. Velocity is a vector quantity and speed is a scalar quantity. Class, what is a vector quantity?
And sir, please, a vector quantity is distance in a specified direction, whilst scalar quantity is distance in all directions.
No, what you are saying is correct, but it's only can be connected to one particular quantity, which is displacement.
Okay.
So a vector quantity is any quantity with both magnitude and direction. So a quantity with a certain amount and direction. Okay, when we talk about force, when you apply a force on a table, the table moves in the direction of the force. Okay, so a force has a certain quantity, and then it also has direction. Okay, our weight.
Yes,
when you want to check your weight, the instrument is placed under your feet. It means that your weight has a direction downwards. Have you ever questioned why we don't put the device on our heads, but we always put it under our feet? Because weight has a direction. It follows the direction of force of gravity. So it is downwards. Class, are you with me?
yes, sir.
So a vector quantity has both magnitude and direction. An example of it: force, weight, velocity, acceleration, moment, momentum, impulse. We have a lot of them. Then a vector quantity, a scalar quantity, only has a magnitude but no direction. Okay, example, time. It will be shocking to hear somebody, oh, what's the time? Then the person say, oh, it is 12 o'clock north. You wonder why north? Because direction has nothing to do with time, isn't it?
Yes, sir.
How much do you have in your pocket? I have 50 Ghana cedis west. Oh, I'm imagining going to the hospital and the nurse, after taking your body temperature, right, the temperature is 37 or 36 degrees Celsius west. You see, these are quantities with no direction. An example of it is mass. More examples: scalar quantities, mass,
energy, pressure,
time,
density,
temperature, amount of substance. So they have only magnitude and no direction. So let's apply that to velocity. Velocity is distance in a specified direction. When you talk about distance and then our direction, okay, the quantity changes from just distance to displacement. So direct me to your house. Oh, my house is 100 meters due north. Once you add direction to the 100 meters, it changes from just distance to displacement. So velocity is displacement over time. Displacement over time. Meaning, in this particular, or with this particular quantity, the direction is very important. And the moment you add direction to distance, it changes to displacement. Class, I hope you are following.
Yes, sir.
Benedict,
yes,
Vincent, Anefi, Cromwell. I wish I can mention all the names. Okay, so now The dimension of distance and displacement are not different. They are the same. They are all length. So capital L. Dimension of time still remains capital what?
T.
Good. So the dimension of velocity is L T to the power -1. Is that okay?
Sir, please a question.
Okay, go ahead.
Sir, please, you were like all dimensions must be in a bracket. But
Yes.
I think I don't see any
This is,
for the.
you see, I have
variable.
indicated velocity in a square bracket, meaning I'm looking for the dimension of velocity. So the dimension of velocity includes the dimension of this displacement over the dimension of time. Okay. Now the next thing is that what's the dimension of displacement? It is capital L. What's the dimension of time? Capital T. That is why the letter representation isn't in a square bracket. I must put the quantity in a square bracket instead. Is that okay?
Okay, sir.
To show that this is about the dimension of velocity.
Okay.
All right, go. Thanks for the question. Please be asking questions. If you are not clear with something, do not hesitate to ask, okay?
Okay.
So, dimension of velocity is LT exponent -1. Let's then determine the dimension of acceleration. Dimension of acceleration. Before we do that, let's understand what acceleration means. What is acceleration?
Sir, please. Acceleration is a change in velocity with respect to time.
So you are right, but practically, what does it mean?
It's
if you are to
velocity
explain
over
that,
time.
Come again.
Velocity over the time taken.
But what is it practically? How would you explain this to somebody? That this is what you see. What you are giving me
as the change of speed.
Change of speed.
How fast an object's speed or direction changes in real life.
Okay, that's good. That's good. All right, so let's go this way. If a body is stationary or at rest, what is the body's speed? If a body is stationary, the body's speed is 0, isn't it?
Yes, sir.
Yes, sir.
Now, when that same body starts moving, is the speed still 0?
No,
Sir.
sir.
When the same body starts running, is the speed changing?
Yes, sir.
So before,
yes,
the body was at rest or was stationary, where the speed was 0. The body started moving, where the speed began to increase. Then the body started running, where the speed is increasing the more. So we see a changing speed of the body with time. So when the body is moving in that manner, as the body speed continues to change, or the change can be an increasing speed or decreasing speed, then we say the body is accelerating. So cars have what we call accelerator. Okay, that pedal on which drivers press changes the speed of the body. That is why it is called accelerator. Are we okay?
Yes, sir.
Yes.
So acceleration is the rate at which a body's speed or velocity changes with respect to time. Class, can a body be moving yet its acceleration is said to be 0?
No.
Listen to the question again. I'm repeating the question. Laura, are you there?
Yes, please.
You are the only lady in the building. So
Okay.
the question is that, can a body be in motion yet its acceleration be 0?
Yes.
So,
Yes? No, sir. Who are those saying yes?
Hi.
Defend your yes. And if he. Can a body be in motion yet its acceleration be 0?
Yes. Yes.
Explain.
The acceleration can be defined as the change of speed. Well, if that object still maintains its speed, there is not experiencing any form of any form of acceleration, which is 0. It's still maintaining its speed.
Okay, that is. I'll give the verdict afterwards. Who are those saying no?
Say yes.
You belong to the yes group.
Yes.
Who are those saying no? If you are saying no, let me see you. My video is on. Yes. Oh. Go explain.
So according to the definition of acceleration, they said it's the change in speed or direction over time.
The change in speed or velocity.
Yes, over time.
With respect to time. Okay.
Then let's take, for example, a train is moving in a straight line at a constant speed and it's moving, but acceleration is 0. It means that there's no change in speed. The speed is constant, direction constant, motion is constant, and the acceleration it means is 0.
Okay, so you are also in support of what Anefi and Co said earlier. Yeah, so
yes.
It is yes. A body can be in motion or can be moving, yet its acceleration can be 0 because acceleration is changing speed. And so if the speed does not change, okay, there will be no acceleration. This is practically, we see that during athletic competitions. Somebody can be very good when the event starts. Somebody can start the motion in such a way that he or she can maintain the speed from start to finish. So see, he has been able to maintain the starting speed till he or she finish the race. And so in this particular scenario, the person's acceleration is 0 because he's been able to maintain the speed throughout. Okay, so a body can be in motion, yet its acceleration can be 0. Okay. Now, the next question is that, okay, when we come to linear motion, we'll talk more about acceleration. So we see that acceleration is the change in velocity, or simply velocity
Over time.
Yes, over time. Yeah. And so the dimension of acceleration becomes, we have the dimension of velocity already, which is T exponent -1 divided by, divided by T. So this will be equal to LT exponent -1 times T exponent -1 again, Don't forget when the denominator comes up, it changes to t exponent -1. And so we have the dimension of acceleration being LT exponent -2. Okay. Let's also use our knowledge of dimensions to find the SI units. L is in meter, T is in seconds, so ms to the power -2. So knowing the dimension of a given quantity, you can also use that to find the, help me find the dimension and SI units of force. So your work is that determine, yeah, the question is determine the dimension of force. Please, can you hear me?
Yes, please.
Okay. The dimension of force and the base unit. And the base of A. Okay. Can you hear me? The question is that determine the dimension of force and its base units. Okay. Determine the dimension of force and the base units. And the base unit. Hello.
Hi.
Okay. The question is on the board.
Sir, please, I'm done.
Okay. Oh, we will discuss it, so don't worry.
Okay.
Please, I'm done.
Please, I'm done.
Okay, so let me put your answers down. What's the dimension of force? Nora, did you finish?
Yes, please.
Okay, so what is the dimension of force? Nora.
M L L T
exponent -2. Okay. Okay, so if you got that right, please mark yourselves. What is the base unit?
Kilogram meters.
Kilogram meter per second.
Kilogram meter per second.
Wait.
So class, yes.
This
is actually the original unit of force. Then we scientists went for a meeting and we wanted to honor Sir Isaac Newton. So instead of calling the unit of force as kilogram meter per second squared, we decided to change this to Newton. That is how come this was changed to Newton, and that became the SI unit. The actual unit of force in terms of the base quantities is kilogram meter per second squared. Is that okay?
Yes.
All right. your two other assignments, which you are doing right away. I want you to determine the dimension of work done, and the base unit. Then finally, the dimension of power and the base unit. So you are looking for the dimension of both and their base unit. So determine dimensional representation or equation and the corresponding base unit. That's corresponding base units. I think 5 minutes to do. Start work done and power.
Sir, please, I'm done.
Who is done?
Kenneth, sir.
Kenneth. Okay, let's wait for our other colleagues. So Kenneth is off. Offer. Are you also done? Offer, are you also done?
Yeah.
You have 2 more minutes to go. True, I think I'll begin to introduce you to higher aspects of dimensional analysis, okay?
Sir, please, I'm done.
Sir, please, I'm done.
Okay, so let's discuss. Nora.
Yes, please.
Are you true?
Yes, please.
Okay. So let's look at it. How did you determine the dimension of work? How did you do it? Vincent. Okay, Nora, go ahead.
So work done is force times distance. And like the dimension for force is MLT raised to the power negative 2. And then the dimension for distance is capital L. So the dimension for work done is ML squared T negative 2.
So ML squared T negative 2. This is the dimension of work done.
Yes, and and the base unit is kilogram meter per second, kilogram meter square per second square. Yes.
So kilogram meter squared per second squared is the base unit. And this was also honored to who?
Newton.
Work done. Work done. This was honored to who?
Joule.
Joule.
Joule. Hey.
Joule. So the SI unit of work done and energy, the same thing. Joule. Capital J. So note that the dimension of work done is the same as the dimension of energy used. Okay. And they all have the same base unit as well as SI unit too. All right. Somebody to take me through how he or she solved power. Power. How did you solve power? The dimension of power.
Work over time.
Come again.
The dimension of power is
work over time.
Or energy over time.
No.
I can hear you. I can hear you.
In the dimension for time power is M L squared T over.
Okay. So since we found the dimension of work done, M L squared T exponent negative 2 time is capital T. And so dimension of power will be equal to what?
ML
squared T
exponent
negative 3. Good. What about the base unit? What about the base unit?
Kilogram.
Kilogram meter squared per cubic second. Kilogram meter squared. Hello.
Per second cube.
Say joule per second.
Oh, I get what you are saying. I'm coming.
But the first one too, you did the same thing.
No, you see, we want to determine the base unit first. Base units. Okay.
Okay.
So the base unit must be in terms of the base, the fundamental, quantities. So you can't say joule per second, even though that's not wrong. But we are expressing this in base units. Class, are we okay?
Yes.
Yeah. Kilogram meter squared per cubic second, or this one. Now, what is the SI unit?
Watt.
Good. So this was named after my good old friend James Watt. Okay. Watt, spelled as this. Don't forget, if you begin with capital letter, then you are referring to the human being watt, not the unit watt. So know the difference. All right. Class, what is the dimension of efficiency? Please, if you are not answering a question, mute yourself, okay? Justin, mute yourself. Zoom user, mute yourself. Justin Oppo. What's the dimension of efficiency? Yes. dimension of efficiency.
Say.
Yes.
Efficiency is dimensionless.
Why? Why do you think efficiency is dimensionless?
Because it's given as a ratio of two quantities with the same dimension.
Very good. Very good. So efficiency is basically work output over work inputs expressed either as a percentage or fraction. So work output, the dimension will cancel out work input. And so efficiency wouldn't have any dimension. And so it's a dimensionless quantity. Class, are you okay?
Yes, sir.
Yes,
all right.
Please.
Now, let's look at using dimension to determine the relationship between two or more quantities. First, the force acting on a body the force, hey, the action is coming before the force. Then the action is forcing the force. The force F acting on a body relates to the body's mass and the acceleration of the body. Derive an equation between these quantities. It is obvious the question wants to establish F is equal to MA. But how would you use dimensional analysis to do this? Before we address this, let me explain this. You see, if a body is moving in a straight line on the road, and you want to calculate the force which is actually moving the body, it is the product of the body's mass and how the rate of change of the speed with respect to time, that is acceleration A. So this A is termed as linear acceleration, the rate at which the body's speed or velocity changes with time, which we spoke about. Okay, class, are you okay?
Yes.
Then, when a body is falling, on the surface of the earth, supposing this is the earth, and the body is falling downwards, and you want to calculate the force with which the body is dropping, okay, to the groundward, then this force becomes the weight of the body. Okay, the force actually doing that is force of gravity. And so that force of gravity, which constitutes the weight, becomes the mass, the constant mass of the body, and acceleration due to gravity. When the body is falling, the rate at which its speed changes with respect to time is constant. The value of, what's the value of acceleration due to gravity? Class, what is the value of acceleration due to gravity? Give me approximate value. Anybody?
Value of
acceleration due to gravity. Hello?
3.
He said, you mean 3?
10.
No.
10.
Yes.
10.
10. Approximately 10 meter per second squared. Nora, are you there?
Yes,
if you don't talk, I'll call you. Okay. What this value means is that whenever a body is falling to the ground, at every 1 second, the speed changes by 10 meter per second. So after every 1 second, the speed, okay, the change in the speed will be 10 meter per second. 10. So it falls with a speed of 10 meter per second within every second. And this value of G is constant so long as we are on the surface of the earth. And so that force becomes G. So that's the difference between, hey, Cromwell, mute yourself, Cromwell. That's the difference between F equal to MA and F equal to MG. MA is used when the body is moving on the surface of the earth. MG is used when the body is falling within the gravitational field. So the body must be in the air, and when it is falling to the ground, that is when we calculate the force dropping it as mg. Is there any question?
Please, a question.
Go ahead.
I said, please, why is it then when you go to the hospital, they said you are checking your weight, but then you are standing, let's say, on the wainscot on the ground instead of being in the air?
Okay, so this value of G, okay, is constant from, in fact, it isn't constant throughout. The further we move from the surface of the earth, okay, affects the value of G though. But within the atmosphere, this G is constant. So let's assume the atmosphere is about 100 or 200 kilometers from the surface of the earth. It means where the 200 kilometers ends, the value is the same throughout to the surface of the where you touch the earth. Your foot makes contact with the earth. That is why in determining the weight, it is still mass times G. So you don't need to be suspended to get G. Once you are on the surface of the earth or within the atmosphere, the value is still the same. Please, have I answered you?
So I'm just saying that when you go to the hospital, they say you are checking your weight.
Yes.
But instead you are not hung freely in the air, but you are standing. Why? When you are standing, is it not checking your mass instead of the weight?
You see, that's what I said though. Your weight is mass times G.
Yes,
and
sir.
the value of G is the same from the atmosphere, where the atmosphere ends, to just the surface of the earth. So when you make contact with the earth, G affects you as well. Okay. Are you okay? That is why
Yes,
you are not supposed to be hanging to get your weight. Our weight is basically effect of gravity on our mass. Our body mass will never change, no matter the location. Okay, but
yes, sir.
The weight can change because gravity varies from planet to planet.
Okay, sir.
Are you okay?
Yes, sir.
Is there any other question? Please ask questions if you don't understand something, or I'll ask you. Okay, so So we are to establish a relationship between F, M, and the acceleration. So in doing this, we say F, which is the force, relates to mass M and also relates to the body's acceleration A. Now in proportionality, whether linear or inverse, when we introduce an equal to, what must follow? When we introduce an equal to, what must follow in proportionality? Come again. A constant. So K. Good. So K, M. Now we don't know the exponential value of M. So let's represent that by a given quantity. It can be A. Okay. We also do not know the exponential value of A. Okay, so this will conflict. So let's change A to X. So let's change the A to X. Then acceleration to Y. All right. The next thing we must do is that you input the dimension of that. What is the dimension of M? The dimension of mass is capital M raised to the power the unknown exponential value. What's the dimension of acceleration? What's the dimension of acceleration? We've done that, so quick.
LT
to the power negative 2. So Y. Okay. Then we simplify K M exponent X L. The power indices, the power affect everything within under the bracket. So L to the power Y, T to the power negative 2Y. Class, are we okay here? Yes. Are we okay up to this stage?
Yes, sir.
Yes.
All right. Then we equate the right-hand side to the dimension of force. Nora, what's the dimension of force? Nora.
M L T to the power negative 2.
Thank you. Is equal to K M exponent X L exponent Y T exponent negative 2Y. So we equate M to M, L to L, and T to T. So M raised to the power 1 here is equal to M raised to the power X in equation 1. So this implies that X is equal to what?
1.
When we compare the exponential value. So we have X. Then L to the power 1, L to the power Y. Clearly, Y is also 1.
Yes, sir.
Okay, and once we found Y, we can ignore the T because it will give us the same value. So when we finish, we substitute our exponential values. F is equal to K M exponent 1 A exponent what? Plus A exponent what?
0.
Y, and Y is also 1. Now when you take the S, the base unit of F, M, and A, you have the constant K to be equal to 1. Do that for me. Take the base unit of F, M, and A, and then find the value of K. Don't forget, we've determined the base unit of force. So when you substitute the base unit of F, M, and A, K will be equal to 1. Prove that for me, class. Just make me proud. Benedict, are you the one?
No.
Somebody is talking, that's why. So have you determined the value of K?
Sir, I don't understand.
I said when you substitute the base unit of F, M, and A. Okay, let's do it. So we have F is equal to K, M, A. What is the base unit of force? Nora, what's the base unit of force? We've done that, so refer.
Newton.
Base unit of force. Newton is the SI unit.
Kilogram meter per second square.
Good. Kilogram meter per second squared is equal to K. The unit of mass is kilogram. Unit of acceleration, meter per second squared. So you realize that kilogram meter per second squared would cancel kilogram meter per second squared. And you have K to be equal to 1. And so if K is equal to 1, then you can say that F is equal to MA. And so we have used dimensional analysis to establish the equation between F, M, and A. Class, are we okay? Class, are we okay?
Yes.
Yes, sir.
All right. I'm giving you one to try. The centripetal force F varies directly to the mass and velocity V of a moving body, and the radius R from the center of a curve and the body. Derive a relationship between F M, V, and R. So derive a relationship between the force acting on the body, the mass of the body, the speed V or the velocity V of the body, and the radius R. Start work. Start work. How many minutes do I give you? Class, how many minutes? Anefi, how many minutes? Hey, everybody is quiet. Okay, I'm giving you 10 minutes. So 10 minutes, and I'll come to you afterwards. Class, is that okay?
Yes, sir.
Yes, please.
3 minutes more. Finished?
Yes, sir.
Nora. Catch her up.
Yes,
No,
please.
Nora, form leader. Nora, automatic class prefect. Finished?
Yes, sir.
No,
Okay.
sir. Yes.
We can also discuss it. Okay, so let's discuss, okay?
Okay.
All right, so.
Sir, please done.
Okay. So, F. Okay, let me first pick your answers. What's the equation?
Sir, please, I had F is equal to MV raised to the power 2 over R.
MV squared
Raised
over R. Yes. Instead of saying raised to the power, MV squared over R.
Over R.
Okay. Any different answer?
Sir, please, you said?
Is there any different answer?
No, sir. Yes, sir.
Okay,
Sir,
let's
the
see.
formula.
Come again.
The formula. Or the
I mean,
relation.
if you had any different answer apart from what is given here. You can share. All right, let's look at it. So F is directly proportional to MVR, meaning F is equal to KMVR, where K is a constant of proportionality. But here the question must clearly define what F, MV, and R represent. And the question has done so. F is force, M is mass, V is velocity, and R is radius. Okay, so K times M exponent X, V exponent Y, R exponent Z. As for the lettering, it depends on you. Then we input the dimensions of M, the mass, capital M, exponent X, dimension of velocity L, T exponent -1 raised to the power Y, dimension of radius. What's the dimension of radius?
Is
L.
L. So whether radius, height, length, okay,
length.
height, whatever, the value is still the same. So those within the bracket must be affected by the exponential power. So L exponent Y, T exponent -Y, L exponent Z. Then you group like terms. M is a Lone Ranger. L Y plus Z, T exponent -Y. Then you equate it to the dimension of force, which is M L T exponent -2 is equal to this. You equate L to L, M to M, and then you find the variables. So straight away, if we equate M, we could see that X is exponent 1, isn't it?
Yes, sir.
Yeah.
If we compare the M, then T, if we equate or compare T, we'll also see that Y is exponent, or Y is equal to 2. Okay, then Y plus Z, when we compare L, Y plus Z I'm coming. Okay, so Y is equal to 2. And when we compare L, Y plus Z would be equal to 1. If Y is 2, then Z, which is equal to 1 minus Y, would be equal to 1 minus 2. And this is -1. Then you go back, you come here to substitute whatever you made for X, Y, and Z. And F would be equal to K, M is exponent X, and X is 1. V is exponent Y, and Y is 2. R is exponent Z, and Z is -1. Now, from indices, R exponent -1 is the same as 1 over R. Please, I hope you know this.
Yes, sir.
Good. So F would be equal to K M V squared then r exponent -1 is equal to, so times 1 over r, which is equal to kmv squared over r. Now, when you take the SI units or the base unit of the quantities, you realize that K would be equal to 1, as I indicated. So pick, this is the right-hand side, this is kilogram meter per second squared. So meter squared per second squared divided by m, and they will cancel out. So if K is equal to 1, then you have F being equal to mv squared over r. You have used dimensional analysis to determine the relationship between given quantities. So this goes to explain the third usage, which is using it to establish an equation between two or more given quantities. Class, is there any question?
No, sir.
All right. So what I'll do is that I'll go through the WASI questions under dimensional analysis and give you about 2 examples to try, so as to, strengthen your muscles on dimensional analysis. Class, is that okay?
Yes, sir.
So I earlier asked you to forward your end of semester questions to me. Please do so. I'll go through. If there are areas I need to teach before we start the program for the semester, we treat that as quickly as possible. So Benedict and the rest of you, I'll be waiting. Nora, if you have any question, end of semester questions, form 1, you can also forward it to me for consideration. Okay.
Okay.
And if you were also given topics to read during the semester, send it to me so that I'll include that in my plan as well. Today we'll end here, but please tell your friends, physics, we are more than serious. As for physics, I assure you, you are going to enjoy it. So please advertise our online program to your colleagues so that they join us. We have a class tomorrow. I want to see all of you in your numbers and then on time. Today, in fact, your attendance wasn't proper. The timing was very, very wrong. I expect that tomorrow you join on time so that we do the needful. Until tomorrow, may the good Lord be with you, protect you, guide you, and help you in all your endeavors. Bye-bye, and extend my greetings to your parents. Okay?
Yes, sir.
Bye-bye. I'll share the video so that you can use that as a revision. Okay.
Okay.